Okay, starting. You get close. Okay, close. Now, hold on, wait a minute. You finished?
I'm filming last minute.
All right.
Deep beneath the forests of Arkansas and the rocky hills of Colorado lies something extraordinary. A treasure that's not gold, not diamond, but something even more powerful. A crystal so pure it vibrates with energy. A mineral that keeps your watch ticking, your phone running, your computer thinking. It's quartz. One of the most abundant minerals on Earth, yet also one of the most valuable. This is the incredible story of how America extracts and transforms quartz crystal, nature's most powerful crystal, from the Earth. Before we dig in, make sure to like, subscribe, and hit the bell to join us on more mind-blowing journeys through the factories, mines, and processes that shape our modern world. Quartz has been part of America's natural story for centuries. Native Americans once used it for tools and spiritual ceremonies, believing it carried the energy of the earth. But the true potential of quartz wasn't discovered until the 20th century, when scientists realized this mineral could do something astonishing. It could generate electricity when pressed. This phenomenon, called piezoelectricity, made quartz one of the most important materials in modern history. During World War II, the US government urgently needed pure quartz crystals to build radios, radar, and navigation equipment. That's when the small town of Mount Ida, Arkansas became a global hotspot. Geologists discovered enormous quartz deposits hidden beneath its hills. Crystals so clear, so perfect, they could be used directly in electronic circuits. By the 1950s, Arkansas was known as the quartz crystal capital of the world. Today, it remains one of the few places on Earth where optical-grade quartz can be mined in massive quantities. Every year, hundreds of tons of quartz are extracted from these mines, some destined for jewelry and museums, others purified and melted into silicon for the chips that power your smartphone or spacecraft. Quartz crystal doesn't just sit on the surface waiting to be picked up. It forms deep underground, inside veins of hot magma that cooled millions of years ago. In places like Hot Springs National Park and Mount Ida, geologists search for signs of these quartz veins using satellite imaging, seismic mapping, and drilling core samples. When a potential deposit is found, crews use drilling rigs to extract small cylindrical samples of rock. If the samples glisten with clear, glass-like crystals, it's time to bring in the big machines. Mining companies clear the topsoil and overburden, revealing the quartz-bearing layer. A hard mixture of clay, granite, and shimmering crystal veins. At first glance, it looks chaotic. But inside these veins are clusters of hexagonal quartz crystals, each formed over millions of years, growing atom by atom in silence. Once the mine site is mapped, the real work begins. Bulldozers and excavators carefully dig into the deposit, breaking open the rock layer where the crystal pockets, called vugs, are found. Unlike coal or iron mining, quartz extraction requires a gentle touch. One wrong move, and a crystal worth thousands of dollars could shatter instantly. So instead of explosives, workers often use pneumatic chisels, diamond saws, and even their bare hands to slowly uncover the sparkling treasures hidden inside. Each day, tons of quartz-bearing rock are moved, sorted, and examined. And when the sunlight hits the first exposed cluster, glowing with perfect transparency, it's a sight that never gets old, even for the miners who've seen it 1,000 times. Once the quartz crystals are extracted, they're covered in red clay, iron oxide, and dust. They look dull and ordinary until the cleaning begins. At the washing stations, massive tanks and high-pressure hoses blast away the dirt. Then the crystals are soaked in acid baths, usually oxalic acid, which dissolves the iron stains and reveals their natural clarity. Workers wear protective gloves and goggles as they carefully clean each crystal, some as small as a fingernail, others as large as a human torso. Every year, American mines produce hundreds of tons of quartz crystal, and about 70% of it is used in electronics, glass, and solar panel production. What's left, the gem-quality crystals, are sold to collectors, jewelers, and tourists. In Arkansas, entire families visit Dig Your Own mines, where you can pay $25 a day to unearth your own crystal treasures under the southern sun. Now that the quartz is cleaned and sorted, its real transformation begins, from natural crystal to technological powerhouse. Quartz's most extraordinary property is its ability to vibrate at a stable frequency when an electric current passes through it. That's the secret behind every quartz watch, radio, and smartphone. At processing plants, quartz crystals are cut into thin wafers using diamond saws. Each wafer is just a fraction of a millimeter thick, thin enough to flex, but strong enough to hold a perfect vibration. These wafers are then placed between electrodes and tested for resonance. A single quartz crystal can vibrate 32,768 times per second, which is why your digital clock ticks with perfect precision. But that's only part of quartz's journey. Crushed quartz, refined to 99.999% purity, becomes the foundation of silicon wafers, the base material for computer chips, solar cells, and fiber optics. At high temperatures, over 1600 degrees, quartz sand is melted into a molten liquid, then cooled into rods, tubes, and wafers that will later power our technology. This connection, from a crystal buried in an Arkansas hillside to the processor in your laptop, is one of the most mind-blowing links between nature and human innovation. Every device we depend on today, from airplanes and GPS satellites to electric cars, owes part of its existence to quartz. In other words, a piece of the earth keeps our modern world in sync. From the red clay hills of Arkansas to the clean rooms of Silicon Valley, quartz has shaped our past and continues to power our future. It's the crystal that hums beneath your fingertips, that keeps time ticking, that connects satellites circling above. All from a simple stone born deep inside the earth. If you enjoyed this journey inside the supergiant quartz crystal mining, make sure to like, subscribe, and turn on the bell, so you never miss another look into the world's most fascinating industries and natural wonders. Because sometimes, the most extraordinary technologies begin with something as simple as a crystal. Beneath the dry deserts, rolling plains, and ancient seabeds of our planet lies a hidden treasure. Not gold, not diamonds, but something far more essential to life itself. A mineral so vital that without it, global agriculture would collapse and billions would go hungry. This is the story of phosphate, the backbone of modern farming and the unsung hero that feeds the world. Today, we'll journey deep inside the supergiant phosphate mines, where ancient rocks are blasted, crushed, and transformed into the nutrients that power our food chain. From prehistoric oceans to high-tech fertilizer plants, this is the mind-blowing story of how we mine and process one of Earth's oldest and most important minerals, phosphate. Before we dive in, Don't forget to like, subscribe, and hit the notification bell for more incredible documentaries about the materials that power our world. Phosphorus, the key element in phosphate rock, is one of life's building blocks. It's in our bones, our DNA, and the energy molecules inside every living cell. Without phosphorus, plants can't grow, cells can't divide, and food simply can't exist. Millions of years ago, ancient marine organisms lived and died in shallow seas. As their remains settled to the ocean floor, they formed thick layers of sediment. Over eons, pressure and time turned these layers into vast phosphate deposits, geological time capsules of life itself. Today, those same layers, once part of prehistoric seas, are being unearthed by human hands to feed the modern world. In modern agriculture, phosphate is indispensable. It's one of the 3 essential nutrients, alongside nitrogen and potassium, that make up the fertilizers feeding our crops. From the wheat in your bread to the corn that feeds livestock, every harvest depends on phosphorus. Yet, the Earth's accessible phosphate resources are limited. To meet the global demand for food, massive open-pit mines have been carved into the Earth, where machines the size of buildings dig deep into ancient rock formations that once lay under primeval seas. Each year, over 200 million tons of phosphate rock are extracted worldwide. Much of it from supergiant deposits in Morocco, China, and the United States. But how exactly do we turn ancient rock into the nutrients that sustain billions of people? Let's step inside a supergiant phosphate mine. The journey begins long before the first explosion shakes the ground. Geologists spend years, sometimes decades, studying maps, drilling samples, and analyzing rock chemistry to find the perfect spot. They look for phosphorite formations, sedimentary layers rich in calcium phosphate, usually remnants of ancient marine life. From satellite imagery to deep drilling, every step helps scientists pinpoint where the richest seams lie hidden below the surface. Once a promising deposit is found, the mining operation begins. At supergiant open-pit mines, entire landscapes are reshaped. Massive excavators, bulldozers, and draglines strip away layers of overburden, soil and rock that cover the valuable phosphate bed below. When the phosphate layer is finally exposed, it's time for controlled blasting. Engineers drill holes into the rock, pack them with precisely measured explosives, and detonate them in sequence. A thunderous roar echoes across the desert as the ground heaves, releasing millions of tons of shattered rock. Now the race begins to move this mountain of material. Colossal haul trucks, each taller than a 2-story house, rumble across the mine floor. Each one carries up to 400 tons of broken rock in a single trip. Excavators with buckets, the size of small swimming pools, scoop up the blasted phosphate ore and load it into trucks, bound for the primary crusher. From above, the mine looks like a giant staircase, spiraling deep into the earth. Each step representing millions of years of ancient biology, now turned into rock. Most of what's dug up is waste. Only a small percentage contains the valuable phosphate minerals. At the processing plant, the rock begins its transformation. Gigantic crushers reduce boulders into fist-sized fragments. Then, massive grinding mills, rotating cylinders filled with steel balls, crush the material even finer, until it becomes a powder resembling sand. This fine material is mixed with water to create a slurry. The first step in separating phosphate from the unwanted rock. It's astonishing to think that every grain of this slurry once came from microscopic organisms that lived hundreds of millions of years ago. Now the science begins. The goal: to extract phosphate minerals from the surrounding impurities. The slurry is pumped into flotation tanks, huge vats where air bubbles are introduced. Chemical reagents are added to make phosphate particles attach to the bubbles and float to the surface, while waste material sinks to the bottom. This process, called froth flotation, is both an art and a science. Operators constantly monitor bubble size, pH levels, and reagent dosage to ensure maximum recovery. What rises to the surface is a phosphate concentrate, the lifeblood of fertilizer production. The concentrate, now thick and muddy, still contains moisture and impurities. It's pumped to filters or thickeners, where excess water is removed. After drying, the result is a powder rich in tricalcium phosphate, the raw material that will soon be turned into fertilizer. For every ton of concentrate, several tons of waste rock, called tailings, are left behind. These tailings are stored in massive ponds or used for land reclamation, where engineers work to minimize environmental impact. Phosphate mining requires a delicate balance, extracting what the world needs while protecting the land. Next, the phosphate rock travels to chemical plants, where chemistry turns stone into something that can feed life. First, the rock is mixed with sulfuric acid in giant reactors. This releases phosphoric acid, a concentrated form of phosphorus that plants can absorb. The reaction also produces gypsum as a byproduct, a chalky material often used in construction or soil treatment. Each batch undergoes strict quality control to ensure it meets agricultural standards. What began as ancient sea life has now become nourishment for the crops that feed humanity. Once processed, phosphate fertilizers are shipped worldwide, by rail, by sea, and by road. From massive ports in Morocco to inland distribution centers in India, Brazil, and the United States, phosphate moves across continents to farms both large and small. Each grain of fertilizer represents a link in the global food chain, connecting miners, chemists, farmers, and families. It's estimated that over half of the world's food production depends on phosphate-based fertilizers. Without them, our planet could feed only a fraction of its current population. As the world's population surges toward 10 billion, the demand for food, and therefore phosphate, continues to rise. But phosphate is a finite resource. Experts warn that easily accessible deposits could peak within decades. The challenge for humanity is clear. We must innovate, recycle, and manage phosphorus wisely, or risk exhausting the very foundation of our food system. From precision agriculture to advanced water treatment, every new technology brings us closer to a sustainable phosphorus future. If you enjoyed this journey inside the hidden world of mining, make sure to hit that like button, subscribe, and tap the notification bell, so you'll never miss our next exploration into the industries that power our planet. Have you ever held a sapphire in your hand? That brilliant blue stone sparkling under the light isn't just a gem, it's the product of millions of years of nature's work and decades of human effort. Today we're taking you deep inside the world of supergiant sapphire mining, from rugged mountains in Montana to cutting-edge processing facilities, to see how one of the world's most valuable gems is found, extracted, and transformed into treasures that last for generations. Before we dive in, Don't forget to like, subscribe, and hit that notification bell for more fascinating behind-the-scenes journeys of how the world's most valuable materials are made. Sapphires aren't just beautiful stones. They're a type of corundum, a mineral made of aluminum oxide, and they rank 9 out of 10 on the Mohs hardness scale, just under diamonds. What makes sapphires special is their trace elements. Tiny amounts of iron and titanium give them that deep, royal blue color. Other trace elements can make them pink, green, yellow, or even colorless. In the US, the most famous sapphires come from Montana, a state often called the Treasure State. Here, sapphires were first discovered in the 1860s by gold miners. They weren't looking for gemstones, they stumbled upon them while panning for gold. But soon, sapphire fever spread. By the late 19th century, the famous Yogo Gulch deposit was discovered. Yogo sapphires are legendary, prized for their uniform cornflower blue color, exceptional clarity, and the fact that they don't need heat treatment to enhance their beauty. From royal crowns in Europe to engagement rings in the US, sapphires have always carried an air of mystery, wealth, and prestige. Imagine standing in the wide-open landscapes of Montana. Rolling hills, gravel bars along the Missouri River, and rugged gulches carved by ancient glaciers. This is sapphire country. Sapphires are typically found in placer deposits, where ancient rivers carried them down from eroded mountain rocks. Over time, the heavier sapphires settled in gravel beds waiting to be discovered. To locate sapphire-rich areas, geologists study the land, analyzing sediment layers and rock formations. In modern mining operations, giant excavators and dredging machines are used to scoop up tons of gravel and sediment. Every shovelful could contain sapphires, but the odds are small. On average, miners might move hundreds of tons of rock to find just a handful of quality gems. That's what makes sapphire mining both a gamble and a wonder. Now let's head inside a supergiant mining plant. Massive bulldozers dig up sapphire-bearing gravel, sometimes working through layers that are millions of years old. The raw gravel is loaded into washing plants. High-powered water jets separate lighter material from heavier stones. Sapphires, being heavier, settle at the bottom along with other dense minerals. Workers and machines sift through the concentrate, looking for flashes of blue, green, or yellow, the telltale sparkle of a sapphire. The excitement of finding a sapphire hasn't changed much since the gold rush days. Each discovery feels like unearthing a hidden star from the earth. A rough sapphire doesn't look like the sparkling gemstone you see in jewelry stores. It's often cloudy, irregular, and dull. Here's how it's transformed. Grading. Experts examine the rough stone for color, clarity, and size. Cutting. Skilled lapidaries use diamond-tipped saws and precision machines to cut the stone. The goal: maximize brilliance while minimizing weight loss. Polishing. Facets are polished to perfection, unlocking the sapphire's fire and sparkle. Heat treatment. Optional. Some sapphires undergo controlled heating to enhance their color. But remember, Yogo sapphires from Montana are naturally beautiful and rarely need treatment. The result? A gemstone that can fetch anywhere from a few hundred to tens of thousands of dollars per carat. While sapphires are famous in jewelry, did you know they also power modern technology? Industrial sapphire glass. Scratch-resistant, used in watch faces, smartphone screens, and scientific instruments. Laser technology. Sapphire crystals doped with titanium create powerful blue lasers. Electronics. Thin sapphire wafers are used in semiconductors and LED manufacturing, so sapphires aren't just about beauty. They're also about science and progress. Behind every sapphire is a story of people. In Montana, mining towns grew around sapphire deposits. Families worked the gravel bars together, passing down stories of luck and discovery. Lapidaries, the skilled craftsmen who cut and polish gems, dedicate years to mastering their art, turning rough stones into dazzling treasures. Jewelers and designers then carry the final product to customers around the world, where sapphires symbolize love, loyalty, and wisdom. Mining also brings challenges, balancing economic opportunity with environmental responsibility. Modern operations focus on land restoration, water recycling, and sustainable practices to protect Montana's natural beauty. Think about this. A sapphire you might see in a ring today could have formed over 500 million years ago, deep within the Earth's crust. From its birth under extreme heat and pressure, to its discovery in a Montana gravel bed, to its transformation in a cutting workshop, that journey is nothing short of extraordinary. Thanks for watching, and until next time, keep discovering. Every day, millions of machines quietly keep the world running. Electric cars, elevators, washing machines, industrial robots. At the core of nearly all of them lies a single essential component: the electric motor. But what powers the motor itself? How is it made, and where do the raw materials come from? In this documentary, we step inside a state-of-the-art facility to uncover the full journey, from recycled metal scraps to precision-engineered electric motors. It's a story of molten metal, spinning copper coils, cutting-edge robotics, and sustainable innovation. You'll witness how scrap metal is recovered, melted down, and reshaped, and how advanced manufacturing techniques transform these raw elements into the motors that drive modern life. This isn't just about engineering, it's about the future of power, production, and the circular economy. This is the incredible manufacturing process of electric motors and the metal recycling revolution behind it. Every electric motor begins its life not on an assembly line, but in the scrapyard. Tons of discarded metal, from old appliances, demolished vehicles, and industrial waste, arrive at recycling centers every day. What once was broken and forgotten is now seen as raw material for the next generation of machines. The first step is sorting. Using powerful magnets, conveyor systems, and infrared scanners, metal is separated by type: ferrous from non-ferrous, steel from aluminum, and copper from brass. Precision is critical. Even a small impurity can affect performance in later stages. Once sorted, the metals are cleaned of dirt, oil, and coatings. Then they're shredded into smaller fragments and sent to furnaces where they're melted down. Aluminum melts at around 660 degrees Celsius, copper at over 1000 degrees, and steel at an even higher temperature. Inside the massive induction furnaces, the scrap metal becomes molten, glowing with intense orange heat. Impurities rise to the surface and are skimmed off as slag, leaving behind purified metal, ready to be reborn. The molten metal is cast into standardized forms: rods, sheets, or billets, depending on the motor component it's destined to become. Aluminum may be rolled into housings, copper into winding wire, and steel into rotor shafts. Before these materials even reach the motor assembly line, they've already been through fire, force, and filtration. It's a transformation few see, but one that underpins every step of modern manufacturing. The journey from junkyard to high-performance component has only just begun. At the center of every electric motor are two vital components: the stator and the rotor. Together, they form the beating heart of the machine, converting electrical energy into mechanical motion with remarkable efficiency. Once the raw materials have been purified and shaped, they move into the precision engineering phase, where each part is carefully manufactured to tight tolerances. Let's begin with the stator, the stationary part of the motor. It typically consists of laminated steel sheets stacked together to form a hollow cylinder. These sheets are stamped with slots that will later house copper windings. Lamination is crucial. By stacking thin layers instead of using a single block of metal, the motor reduces energy loss caused by eddy currents, improving overall efficiency. The stator core is placed in an automated winding machine. Here, insulated copper wire, usually made from 99.99% pure recycled copper, is wound into tight, uniform coils that fit into the slots. These coils are not randomly wound, they follow a precise configuration based on the motor's design. Whether it's a three-phase industrial motor or a small DC motor for a household appliance, The winding pattern defines how the magnetic field will be generated. After winding, the coils are dipped or sprayed with varnish, then baked in industrial ovens. This insulation process ensures that the wires remain fixed and protected from moisture, vibration, and heat during operation. Next comes the rotor, the rotating part of the motor. Depending on the type of motor, it may consist of solid steel shafts, laminated cores, or even cast aluminum squirrel cage designs. In induction motors, for example, molten aluminum is injected into molds around a rotor core, forming conductive bars that interact with the magnetic field from the stator. Balancing is critical at this stage. The rotor must spin at thousands of revolutions per minute without wobbling. High-precision machines check for even the smallest imbalance. If necessary, micro-adjustments are made by shaving material or adding weights to achieve perfect symmetry. Bearings are then installed on each end of the rotor shaft. These reduce friction and allow smooth rotation while also handling the mechanical loads during operation. Depending on the application, the bearings might be sealed, ceramic, or even magnetic for ultra-low resistance performance. Once the stator and rotor are completed, they undergo separate quality control inspections. Electrical tests check for coil resistance, insulation integrity, and potential short circuits. Mechanical tests verify alignment, dimensional accuracy, and overall structural soundness. It's only when both components pass all tests that they move to the assembly phase, where the motor will finally take shape. Building stators and rotors